Nearly 20 years ago, I had a life-altering experience. A number of seemingly random events led to that moment. The first event, I attended my first Signal Integrity Conference in the spring of 2005 because of my concern about my level of expertise and that of my customers. There, I was fortunate enough to meet Rick Hartley, who immediately shook up my comfortable circuit theory-based world. The second event, Freescale planning its first worldwide customer event called Freescale Technology Forum for the summer of 2005. And my manager was on the content committee. He asked me to take his place during one of the calls. I was still very concerned about the changes in our technology and the issues I was seeing with signal integrity. So during a lull in the discussion, I declared that we had a responsibility to help our customers become more aware of this issue, and we should provide some training. The response was to task me with creating a panel of experts to address this issue. The third event, I really put my foot in my mouth here. I did not know any experts, but I could not let this opportunity pass by. To make it look like I knew what I was doing, I had been buying books on signal integrity and EMC. And my only recourse was to start calling authors and asking them if they would be interested in participating. One of the books on my shelf was Ralph Morrison's Grounding and Shielding Techniques, which I'd been told was a foundation text for any library. I found the phone number for Ralph, called it, and left a message. Ralph called me back and asked, "Who are you and why are you calling me?" I meekly answered, "My name is Dan Beeker from Freescale, and I would like to invite you to be part of a panel discussion on signal integrity and EMC." After some discussion, I was relieved to have him agree to be part of this event. The game-changing event. Ralph went first, since he was the one with the physics background. His listening to the other speakers led to his famous lament, jumping up and down, saying, they've got it wrong, that's not how things work." That was the event that shook my personal and professional world. From that moment, Ralph became an integral part of my life, sharing his knowledge and insight into the world of electromagnetic physics with me. His dedicated and caring approach to bringing me away from the dark side of circuit theory into the realm of real science led to a friendship that enriched my life. The bonus was meeting Elizabeth and being introduced into the world of music they shared, finding that I now had two very dear friends who became like family to me. From this first meeting, I took every opportunity I could to spend time with Ralph. I was able to contract him to teach his words of wisdom to my customers in Detroit, and he became a perennial contributor at the Freescale Technology Forums. These events allowed me to spend time with Ralph, slowly absorbing his wisdom. Ralph was patient, spending many hours with me discussing his perspectives on the science. I attended every one of his lectures, and whenever I traveled to the Bay Area, I made sure to plan a visit with Ralph and Elizabeth. An extra bonus was getting to share their music as they played with their friends in their home. One of the highlights of my life was a moment when Ralph declared, after listening to one of my presentations, "Dan, I think you finally got it." I was thrilled. Ralph often said I was the only person who listened to him. I find that to be a real mystery, as the insight and knowledge I gained from Ralph's patient mentoring completely changed my career. Adopting Ralph's perspective on electronics enabled me to become one of the most successful designers at my company. And more importantly, he provided me with a new set of rules to pass on to my customers. These rules are based on the simple statement Ralph had always used to end his seminars. Buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. This was the missing link between electromagnetic field physics and circuit theory, missed by academia and industry alike. Once I could truly trust the simple fact, all the mystery disappeared and the true brilliance of Ralph Morrison became evident. I am honored and humbled by his appointment as his apprentice, and mourn the loss of my friend and the loss to the world of so much more we failed to glean from his profound knowledge. I will miss our talks, our tie outings, his lectures when I used the wrong word, and his support.
Back when I was a youngster, I saw that friends had crystal sets, and and I got my mother to put up the few dollars to buy a crystal set. I was enamored with radios and with things that made that radio work. I remember the very first radio the family got. It impressed me that information and music and whatever came through the airways in some way, and I wanted to understand that kind of mechanism.
So now I would like to introduce Elizabeth Morrison, my friend and Ralph's strongest supporter.
Thank you, Dan. I'm here to say a few words about Ralph's life so you'll know the background of that man jumping up and down and talking to Dan Beeker at that momentous occasion. But first, I'd like to say how happy it made Ralph to have Dan and also Ken and Rick recognize and use his ideas in the real world. It was his mission in life to bring the principles of physics to the electrical engineer. He had not given up on his mission before he met Dan, but I do think he was beginning to wonder if it would happen in his lifetime. Ralph was born in the Highland Park section of Los Angeles. His parents were immigrants from Ukraine. They were far from well off, but thanks to good public schools, he received an excellent education. He graduated from Eagle Rock High School, which is an international baccalaureate school, in 1943. And the Second World War was in progress, so he was drafted immediately after graduating. This made actually his whole class of 43 extraordinarily close throughout their lives. In 2018, we attended his 75th high school reunion of Eagle Rock High School. After his service and a year spent traveling around Europe as a violinist with the GI Symphony, he was able to enter Caltech on the GI Bill. His degree was in physics, as Dan said, and his studies there laid the foundation for his thinking throughout his career. He was a working engineer. He built and sold lots of instrumentation, as you can see him doing in this photograph, but he was always thinking about physics and questioning whether the assumptions of circuit theory in particular made sense. While working, lecturing, teaching, and consulting, he somehow found time to do a lot of writing. By the time he sold his last company, which was called Instrum, in the early 90s, he'd already written 4 books and brought out 3 editions of his groundbreaking book, Grounding and Shielding in Instrumentation. After retiring, he continued to lecture and consult. He wrote 4 more books and brought out 3 more editions of Grounding and Shielding. That's a new edition each decade from the 1960s into the 21st century. His default setting for most of our marriage was to get up each morning, work a Sudoku puzzle, go to his computer, and write another book. His final work, which was called Fast Circuit Boards, was published in 2018 when he was 93. Ralph's other passion was music. He began violin at age 4. His mother had taken up the instrument while expecting his younger sister, and Ralph said he wanted to play too. So his father found him a toy violin. He threw it on the floor. He did not want a toy. Somehow a quarter-size violin was found for him, and he never stopped playing his whole life, even during the war. The photo on the left shows him in the GI Symphony. After returning home, he joined an ensemble led by Julian Brodetsky. This is the photo on the bottom, which is where he first met the late Beethoven quartets, which were his joy throughout his life. The photo in the text shows him preparing for a violin recital he gave to celebrate his 90th birthday. Ralph and I met playing a Beethoven string quartet. We played so much music together over the 30 years of our marriage. Ralph loved sharing music with friends, and it was a source of great pleasure to both of us. When Dan would visit us, he always asked to hear us play, and we were always glad to do so. Ralph was a wonderful musician, a wonderful engineer, and a wonderful husband.
One of the things we were able to do, because in my opinion, Ralph had been one of the most underappreciated engineers and scientists in our industry, was I brought to the attention of NXP management that we had a wonderful opportunity during one of our conferences in Silicon Valley to honor Ralph. When I presented this idea to the managers, they were absolutely 100% behind this. And one of our marketing managers then proceeded to deliver a Lifetime Achievement Award to Ralph. And this is a picture of him receiving that award.
But Dan's needs were with specifically the problem of printed circuit boards. And he was from a school of thought that where there was a lot to learn. I had a lot to learn. But from my experiences, I could tell that what they were talking about didn't match the physics I understood. Little by little, I appreciated his problem, and I learned what their problems were. I am not a circuit designer in the logical sense. I had built lots of circuits, but not logic circuits. However, all of it is electronics. All of it is field theory when you get down to what the interference problems are. And little by little, my understanding grew to the point where I could really sense what was happening and what was needed in the explanations as to how this world works and what it takes to avoid the difficulties they were walking straight into. And it was Dan's interest that drove me to stay connected to these problems. And of course, I would have to say recognition is a very strong factor in how we spend our time and what we do. And when somebody pats you on the back and they say, "You're doing beautifully, you're very much appreciated," you continue doing that.
So this is the book that Ralph wrote after we met. He decided that he was going to take the current technology and apply his perspective. And this was the result: fast circuit boards. Always the central point was his mantra: buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. This simple fact was so heretical compared to the beliefs and teachings of most universities regarding energy in electronic circuits that it was very difficult for me to make the transition from the traditional electrons flowing in wires to energy moving in a space. It took almost 10 years of Ralph's patient tutoring for me to be able to become very confident and secure in the idea that the science was right and following the simple rules that he provided would result in success. So they boil down to a very simple picture here. And when I look at this, to me, it's still very profound. And the idea is that we use conductors to direct the fields. So in a good system design, there are three elements that are used to contain field. There's a conductor, a space, and a conductor. And on the left-hand side, you can see those three elements. It's the rule of triplets. In electronic circuits, you only have three components. You have a conductor, a dielectric, and a switch. So in the middle is the switch. Until the switch is closed, the field energy on the left will be very happy to stay put on the left-hand side. As the switch is closed, the field starts to see a need for it to move into the new space. So a switch, instead of closing a circuit, actually connects a space where the energy is not present. So the field energy really wants to become equal throughout the entire space. So as the switch closes, the field energy will move sequentially into the new space until equilibrium is established. As the energy continues to move through the dielectric, we can control where this energy goes by managing carefully the three elements of the circuit board. One is the continuous conductor, which sometimes we call ground. Adjacent to that continuous conductor must be the continuous dielectric, which is the space where the energy will move. Adjacent to that dielectric is what I call the switched conductor. This is the only thing we get to control in our designs. By using the switches, we can connect or disconnect the spaces where we want the energy to move. When the switch is opened, the energy flow stops, and there will be field energy on either side. And depending on what is at the end of this transmission line, the field will either become static because it's not moving, or it will continue to be moving through the board structure. You can only do three things with field energy. You can store it between two conductors. You can move it as you provide a new space to allow the field energy to move forward, or you can convert it into kinetic energy. And that's basically the entire electronics world. From what Ralph taught me, this is not rocket science. This is some very simple geometry-based rules. And when you think about designing the dielectrics as opposed to designing conductors, the results are nothing short of miraculous. Here's the bottom line. We were taught that when you close a switch, the energy starts moving in a loop through the conductors. If that were true, there would be no issues with signal integrity, and we would have no problems with radiated emissions. But at the same time, there would be no such thing as radio. So every day we prove to ourselves that circuit theory is not a correct perspective, because radio is something that we live with. The energy used in radio is electromagnetic field, and it travels through space. Just because we start to move the same energy on a circuit board, it does not magically change into electrons moving in wires. It is still electromagnetic field energy moving through a space, which hopefully we designed on purpose. When you turn on a switch, you've added a new space, and the energy flows into this new space. So this is the bottom line here. The rules of triplets. You can use one hand 3 times. You only get 3 components to control the energy: a conductor, a dielectric, and a conductor. Field will sit there very happily. There's only 3 components. You get a conductor, a space, and a switch. And again, you can only do 3 things with electromagnetic field energy. You can store it, you can move it, or you can convert it to kinetic energy. You use the energy to heat up wires and make lights work. You use the energy to move motors or to vibrate speakers. Pretty much that's the only thing you can do with it. And if you manage the dielectrics properly, the energy goes where you want it to. If you size the dielectrics properly, you move enough energy to do the work that you need, and your circuit boards and your systems will behave properly. As I said, it's not rocket science. It's very simple applied physics. So what we have to remember is that everything is a transmission line. And it needs to be a transmission line that we created on purpose. It's not the basic circuit point of view, which doesn't care about the space, but just looks at the connection of the conductors. What you have to do is to make sure that you have a specifically and purposefully designed dielectric space, bounded on one side by a continuous conductor and bounded on the other side by the switched conductor that we use to allow the field to move, or we stop the field from moving.
I originally learned of Ralph's teaching through Dan Beeker, who teaches with me during the annual EMC Week training seminars in Boulder City, Nevada. I was also fortunate to be able to participate in what was Ralph's last public seminar on the subject. Later, I attended Rick's 2-day seminar on PC board design and forever became an advocate of the field's point of view for PC board design. I'll be forever indebted to Ralph, Dan, and Rick as we help move product designers towards physics-based board design. With that, I'll continue with my slides here. As Dan mentioned earlier, all board traces and planes are transmission lines. Most of us were probably taught in our DC circuits class that current travels through wires from the source to load and back. And this is true for theoretically pure DC. It may also have been implied that the current travels at or near light speed, which is false. However, once we start to reach beyond 10 kilohertz AC or so in frequency, we need to start thinking in terms of signal propagation as electromagnetic waves. In order to propagate the field energy within the signal's electromagnetic wave, it must be trapped between two pieces of metal. In the usual case, for circuit boards, between the copper microstrip and return plane. So we have the circuit's point of view, where digital circuits and power require a return path back to the source, and we have the field's point of view, where the signal and power transient fields travel in the dielectric space at near light speed, while the conduction and displacement currents simultaneously flow back to the source at only about 1 centimeter per second. Think about wave propagation like throwing a rock into a pond. As the wave radiates out from the point of impact, the waves propagate along the surface. The water molecules don't actually move with the wavefront. They just move up and down in place. And the same basic concept occurs as signals propagate through circuit boards. The important point is that the digital signal energy is in the fields, not the copper. The next slide shows the physics involved. It's important to understand the physics of electromagnetic wave propagation in circuit boards. To understand how digital signals propagate in circuit boards, we first need to understand how current appears to flow through a dielectric layer. Consider the figure on the left. When we close a switch, current will start to flow, building up a positive charge on the top plate of the capacitor. This positive charge repels any positive charges on the bottom plate, thus resulting in negative charges remaining. An AC or digital signal will cause the charges to alternate, thus appearing to conduct current. Maxwell called this effect displacement current. Now, referring to the figure on the right, if we apply a digital signal or wavefront with leading edge going from high to low to the microstrip, an electromagnetic wave will be launched and will begin to propagate through the dielectric space between the microstrip and return plane at about half light speed for the typical FR4 dielectric. As the wave propagates down the microstrip, conduction and displacement currents will be induced via electron flow in the copper molecules. Because copper electrons are pretty tightly bound, there will be electron flow, but at very low speed of about 1 centimeter per second. This is the current we measure with an ammeter. The location of the displacement current will move at near light speed, following along with the wavefront. It is important to note that breaking this return current path will cause field leakage of the electromagnetic wave, generation of common mode currents, and an increase in EMI. I'll show the dramatic increase in EMI as a result of a break in the return plane later in this presentation. As Dan described, the rules of board design are relatively simple. Every signal trace needs an adjacent return plane or trace in order to contain the field. And every power trace or plane needs an adjacent return trace or plane to contain the transient field. Most importantly, this also includes return paths up and down through layers when signals transition from the top to bottom layers. And this would require the addition of ground stitching vias for return-to-return layers and stitching capacitors for return layers. These rules will dictate the stack-up design. And this is where many PC board designs cause EMC compliance test failures. Very few of my clients get the stack-up right. Here's the typical 4-layer stack-up IC. From top to bottom, we have signal, ground return, power, and signal. This is a very risky EMI design, as Rick will mention shortly. The first issue is that for the usual 62 mil thick boards, the power and return planes are spaced too far apart for good high-frequency decoupling. Second, the bottom signal layer is referenced to power rather than ground return. Most digital signals want their return currents referenced to digital ground return rather than power. When referenced to power return, currents must find their way somehow back to the source, and this convoluted path usually ends up causing radiated emissions and susceptibility problems. The only time I relent and allow signals referenced to power is when the power return planes are closely spaced at 2 to 3 mils max and with adequate decoupling capacitors, or if the signals are low frequency. And with 62 mil thick boards, this is not the case. If your budget dictates a 4-layer design, the EMI issues may be fixed by substituting the power plane for a second ground return plane. Thus, we have 2 signal layers with routed power or power polygons and 2 ground return planes. Because we lack closely coupled power and return planes, the most important consideration is to include sufficient decoupling capacitors at the power pins of ICs. There are 2 considerations: placing the 2 return planes on the inside layers, as in the top figure, or placing them on the outside layers, as in the bottom figure. I guess you could also make the stack-up signal return as well. The advantage of having the 2 return planes on the inside layers is that the signal traces are easier to get to for troubleshooting purposes. On the other hand, if the planes are on the outside, they may be stitched together around the edges to simulate a Faraday shield. Most 6-layer board stack-ups I see when performing EMC design reviews are that shown on the left, another poor stack-up design. The top 3 layers, signal, return, signal, are fine as is. The issue occurs in the bottom 3 layers, where again we see the signal layers referenced to power. Also, with the power and return planes separated by up to 40 mils in a 62 mil board, you would expect very poor high-frequency decoupling. Also bad news for EMC. A new problem surfaces though, and that is the fact that there are 2 signal layers between power and ground return. So what do you think happens when we have power transients occurring between the power and ground return planes in layers 2 and 5? That's right, power transients coupling to signal traces in layers 3 and 4. A better design for signal integrity, power integrity, and EMI is the board design on the right. Note that every signal and power layer has an adjacent return plane, so all propagating fields are nicely trapped as the electromagnetic waves propagate from source to load.
Thank you very much, everybody. Before I start on the picture on the screen, I would really love to just take a minute to talk about Ralph. I met Ralph shortly after Dan did. Dan came to one of my talks at PCB West, I believe it was 2006, and he brought Ralph with him. And just as Ralph jumped up and down at the Freescale Technology Forum, he jumped up and down in my class too, saying, "You've got it wrong." And I wasn't quite sure what he meant. And so we ended up having a meal together that day. And over the meal, Ralph said to me, "Rick," he said, "honestly, I really like much of what you presented today. You have a lot of really good material and a lot of really good ideas. However," and there's that word however or but, which means that everything that came before it didn't matter. And he said very carefully and very, very clearly, "You're talking about energy being in voltage and current, and it simply is not in the voltage and current. The energy is in the fields." I'm going to tell you, it took me a long time, just as it did Dan, to shake what I had learned in college and what I had learned from every engineer I worked with over my career. The idea that the energy was in the fields was really tough for me to deal with. It took me literally, and I'm not exaggerating, years to get used to the idea. Once I did, I really began to understand exactly what was going on in the circuit. Suddenly, once I understood fields, suddenly every problem I had seen in my life, I could explain. Up to that point, I had a lot of trouble explaining to people why this problem or that problem occurred. Good example, circuit A and circuit B on the same circuit board have absolutely no copper connections between them. No power, no ground, nothing connecting between them, and yet one interferes with the other. How is that possible? Well, in circuit theory, it would be easy to explain if they were connected. If they aren't connected, circuit theory can't explain that interference, but field theory can. And once I finally understood field theory, suddenly everything in my life made sense, and all the problems I'd seen made sense. And frankly, I've been designing using field theory for many years now and haven't had any problems as a result of it. And I don't expect to at any point in the future. And I just want to take a minute to say how very much Ralph meant to my life. He truly, literally changed who I am, what I am, the way I think, and the way I teach. And people who attend my classes now tell me repeatedly that they gain a lot of really good information because I'm basically teaching them Ralph's thinking and Ralph's theories. And I will forever be humble to that wonderful man. So looking at this 4-layer board, Ken talked a bit about the problems with a conventional 4-layer board with power and ground on layers, pardon me, 2 and 3. And he's absolutely right. There are many problems with that board, one of which is the high impedance power bus, which I will address that in just a moment. In 1995, I was working for Goodrich Aerospace, and we had a very low-cost product that we had to design and build and ship. And it was decided that the main board in it, there was one board and a couple of small boards with power and so on. And the main board was going to be a 4-layer board. So I designed it as a conventional 4-layer board with power and ground on 2 and 3. And we were failing EMI by 6 or 8 dB. I mean, it was horrendous. And we weren't just failing at a frequency, we were failing at a half dozen frequencies or more. It was really bad. The group of engineers in the company, myself included, got together and talked about what we can do about it. And we kicked around a lot of ideas, and someone brought up the concept of, what if we could move the signals from the outer layers to the inner layers? Instead of making them microstrip, make them strip line. And I thought about that and realized strip line are inherently quieter because, and I didn't even realize the concept of fields then, but I knew the energy was better contained with strip line than it is with microstrip. And so I started working on that thought. And I brought the board up on the screen and I disconnected the ends of all the traces where they connected to the components. And I moved the signals from 1 to layer 2. And I moved the signals from 4 to layer 3. And amazingly, when I turned the top 2 layers off where the components were, suddenly, as I looked at these 2 signal layers, I realized, my God, there is a ton of open space on these 2 layers. because they don't have all those pesky components in the way, taking up space. When these signals were routed with the components, between the components and the signals, they consumed every square millimeter of space on both the top and bottom of the board. But when I moved them to the center two layers, suddenly it's amazing how much open space there was. So that's when I got the idea, wait a minute, let's pour ground with copper pour on the top around the components and on the bottom. And the beauty of it was the signals had already been routed in a place away from the components. So all of the signals now referenced, beautifully referenced, that ground pour that I had just put on the board. And then when I was done, I thought, wow, this is great. What am I going to do about power? And then it hit me. I've got all the open space on layers 2 and 3. Let's do copper pour on those layers and make that the power. Well, when I first did it, not every power connection was made because some of the signals got in the way of power pour. I had to move some signals around and do this and do that. But eventually I came up with a design that had signals and power on layer 2 and layer 3 and the ground on layer 4. And it worked brilliantly. And here's the best part. When we went to EMI testing, we got a 14 or 15 dB improvement in the EMI signature. And we passed EMI testing easily with this board. I'm not going to sit here for a moment and tell you that this is an easy design. People who design with signals on top and bottom and power and ground on 2 and 3, they're making their life easy. That's easy to do. Do you want easy or do you want something that will actually work? This is another version of that same board, and Ken talked about this as well. The nice thing about this, as he pointed out, is that you have signals on the outer layers for easy access. The downside to this is that it only works in low density designs. Think about this. You have components, you have signals routed, and you have power all on the outer layer. Now, there's two ways, as Ken pointed out also, you can do power. You can route power in the case of lower frequency components such as microcontrollers and devices that have edge rates that are 2 to 3 nanoseconds. You can route power because you can properly place decoupling to allow you to route power and get excellent results. With higher speed parts, microprocessors and other things, you're really going to have a tough time routing power. You're probably going to have to pour it. So whether you're routing or pouring power, this design on the right works brilliantly, but it only works for low density designs. The one on the left works in many scenarios. Once I came up with this concept of the design A on the left in 1995, once that was realized, I've probably designed 50 circuit boards like that since, and every single one of them has worked absolutely flawlessly. It's just a brilliant design. Ken also mentioned the power bus, the plane impedance, when you have a conventional 4-layer board with power and ground on layers 2 and 3. If you do the board stack up as either of the ones on the previous slide, the power bus impedance improves from the gray line next to the red line. And the beauty of it is that when you put power on 1 and 2 and 3 and 4, in other words, power ground, in any combination, you will improve the power bus impedance by anywhere from 5 to 6 times improvement. This is a logarithmic scale, and this may not look like a massive improvement, but it is a massive lowering of the impedance. So 4-layer boards of that type, again, harder to design, but much superior in their capability. This is a 6-layer board that Ken also mentioned. That's the poor design. And as he discussed, one of the problems is having signals between the power ground planes. And a second problem is having the power and ground planes separated by, in this case, about 50 mils, 45 to 50 mils. That's an enormous spacing. You can take this same board stack and by putting copper pores on the layer 1, layer 3, layer 4, and layer 6 signal layers and attaching those to the power that you need to distribute, you can attach the top 2 pores to ground and the bottom 2 to power. You end up now, instead of delivering power from, and one of the questions I ask people in my sessions that I teach, when I bring up a board like this, where does power come from? And most of the people in the room will say the power plane. The answer to that is incorrect. The energy does not come from the power plane. It comes from the dielectric space between the power plane and the ground plane. The design on the left, the energy gets delivered in the dielectric between 2 and 5, as Ken pointed out. The problem with that is power bus switching transients, as he also mentioned, can couple into signals. With the stack up on the right, power no longer comes from 2 and 5. Power, because of the copper pores, now comes from a dielectric space between 1 and 2, between 2 and 3, between 3 and 4, between 4 and 5, and between 5 and 6. So you get 5, and even though each of those areas is smaller areas of delivery, you end up with 5 much more closely spaced dielectrics delivering power, which drastically lowers power bus impedance. And here's the best part. The signals in the middle of the board, if they're distributed properly, where they reference a plane above and a plane and a power pore section below, those signals are no longer suspect to being interfered with the power delivery from those dielectrics, because now the power is being delivered next to the signal fields, not over top of. And this makes a major difference. This is still not what I consider an ideal 6-layer stack-up, but it is a massive improvement over the previous stack-up. This is the power bus impedance of planes on layers 2 and 5. That would be the board stack we just talked about on the left. This is what happens when you go to the power pores on each of the layers, and now are delivering power from the dielectrics from 1 to 2, 2 to 3, 3 to 4, and so on. The overall response raises the capacitance of the planes and drastically, and most important part, drastically lowers the inductance of the power planes. And the result is this is an order of magnitude improvement. This is a times 10 lowering of the power bus impedance. Is this fantastic? Is this going to work at gigabit speeds? Heavens no. This is not going to work at gigabit speeds, but this is a massive improvement for simpler board designs of the type that many people often find themselves dealing with. This is an 8-layer board stack up that I'm particularly fond of. Most people will put signals, ground, signal, power ground in the middle, signals, ground, signal. To that, I usually add the copper pores on the signal layers, and I alternate them as power and ground. So once again, you're not getting power from just the center of the board. You're getting power from all 7 dielectrics in this board, and it's being delivered through a much lower impedance path, which is a drastic improvement in power delivery, and it keeps the signals away from power and so on and so on. This is another 8-layer design that is a distinct improvement even over the one on the left. The reason we've gotten rid of the power plane entirely, and now everything in the board references ground. The only downside to this is if you must have a power plane to distribute power, if you can't get it done with power pores, then this is going to be a challenge to make work. But as long as you can do it with pores, this is a magnificent stack-up. And this is my favorite 8-layer stack-up. Signal, ground, signal, ground, signal, ground, signal, ground. Every other layer is ground, and everything references ground. You could invert the bottom 2 if you really need for the outer 2 layers to be signals, or you could use the stack up in the middle. I prefer this one on the right. You can take 2 layers away from this and make an excellent 6-layer board as well. You can add 2 more layers just like this and make an excellent 10-layer board. This is an 8-layer stack up, and I'm not going to say who it was, but there's a major IC company. The last project I worked on prior to retiring, we had a 1300 pin microprocessor from a major IC company. And in their 100-page app note, they referenced this board stack up and said, we know some people must have low layer count because of cost. This is the smallest layer count we were able to route this 1300 pin processor on. I can understand that if they had enough on package and on die capacitance that they might have, from a signal integrity point of view, been able to get this to work, but it's clear to me that they did no EMI testing. And the reason I say that, there is not a chance in the world that this board could pass EMI testing. Why do I say that? Look at power plane 1. Where does power from that plane come from? Again, don't say it comes from the copper. It comes from the dielectric between that power plane and the layers above and below it. Some of the fields from power plane 1 will couple to ground, but the majority of them, because of proximity, will couple to power plane 2, which means the majority of the return current from power plane 1 will be in power plane 2. And the same thing is true of power plane 2. Most of its fields will couple to power plane 1. Is this a good idea? I don't think I need to tell any of you it is not a good idea. First time I presented this, a gentleman said to me, it's an 8-layer board, Rick. You have a core in the middle. You can make that core thick and widely separate power 1 and power 2. Correct. But when you do that, now where does power plane 1 couple? To the ground plane on 2. What is in between power 1 and that ground plane on 2? Aha, a signal layer on 3. That means the signal energy is going to couple into the power bus, and the power bus transients are going to couple into the signal. This is an almost guaranteed EMI failure. Every time I do a public forum, public presentation, I mention this company by name, and I say, is there anyone in the audience from this organization? And usually 1 or 2 hands go up. And I say to them, go back to the company, find out who proposed this, prove that you guys did EMI testing and that you passed, and I'll quit talking about you. But until you prove me wrong, I intend to continue throwing your name out in a negative light. This is a 10-layer stack up from a client that I had a couple of years ago who had major problems with the board. When I get a call or an email from someone saying we've got this or that problem, the first question I ask them, what is your board stack up? I took one look at this board stack up and immediately knew what was wrong. The power planes in this board, problem number 1, reference each other. Notice on the center 2 layers, there are signals. Half of each one of those layers were power planes, and they reference the power planes above and below them. So all of the signals on layers 5 and 6 reference the power planes on 4 and 7. That is a terrible thing to do, as we've already talked about. And not only that, the power planes that were on those center layers reference the power planes above. If that's not bad enough, the routes that are on layers 3 and 8 reference power more than they reference ground. So the majority, because of spacing, the majority of their fields are going to be coupled to power planes. And if that's not bad enough, those signals are trapped between the signals on the power and ground on layers 2 and 4, and then again at the bottom of the board. When you look at this, it's obvious. This is everything wrong in the world. Whoever decided in the first place that this was a good board stack up was absolutely not thinking clearly. If that's not enough, as this bottom comment says, the top 2 dielectrics are 2.5 mil prepregs. It's tough to contain and hold prepregs to exactly 2.5 mils. Their intent was to get 50 ohm lines on every layer. And as you can see from the comment on the left of this diagram, the top and bottom layers were 45 ohms. The next signal layers were 38 ohms. And the only place they had 50 ohm lines were in the middle of the board. But of course, those particular lines referenced the power planes above and below. This is a horrendous stack up. You have to think about the fields. Where will the fields exist? As Dan pointed out, as Ken pointed out, signals and power should always reference ground. Think about designing stack ups where that is possible. Thank you very much.
Well, thanks, Rick. Very educational. Aside from the stack-up problems described earlier by Rick and myself, one of the biggest design issues I find during reviews is clock or high-speed digital signals crossing gaps in the return plane. Now, we like to have a solid return plane. So at this point, I usually perform a live demo, but I'll try and do my best with diagrams and an actual measurement result. When we have a clock crossing a gap in the return plane, the gap forces the return conduction current out around the gap. This causes mutual inductive coupling on each side of the gap, which in turn produces a small voltage source that converts the differential mode or signal currents to common mode currents throughout the board. These stray currents tend to escape out I/O and power cables, causing radiated emissions and an increase in susceptibility to things like ESD and radiated immunity and other external energy sources. I've tried to depict the electromagnetic fields as curved red lines between the clock trace and return path. In the next slide, I'll show the test setup. Let's consider a two-layer board with two 50-ohm transmission lines. At one end, we have BNC connectors, and at the other, 50-ohm loads. The top transmission line has a gap cut into the return plane. When I connect a pulse generator with 10 megahertz harmonics to the BNC connector for the ungapped trace and probe along the transmission line with an H-field probe, we'll see a set of harmonic signals spaced every 10 megahertz from the source to the load. Probing the unconnected gapped trace will show very little coupling. So now let's connect the pulse generator to the gapped trace. We'll see an increase of 10 dB in harmonic energy at the gap, but more interestingly, we can see major coupling to the now disconnected ungapped trace. Finally, let's connect a clip lead to the return plane to simulate an I/O cable and measure the harmonic RF currents in the wire. When driving the gapped trace, we'll see an increase of 10 to 15 dB when compared to driving the ungapped trace. This could be the difference between passing and failing the radiated emission test. To see this demo in a recorded video, just click on the link or go to my website, www.emc-seminars.com, and find the Videos tab. This plot shows the difference between driving the gapped versus the ungapped traces. The gap in the return plane is causing common mode currents to form, which then flow out along the attached wire. Placing a current probe around the clip lead shows the high frequency currents flowing through the wire, which cause the wire to become an antenna and radiate. In the spectral plot, we're looking from 30 to 1000 megahertz. The violet measurement is when I'm driving the gapped trace, and the aqua measurement is when driving the ungapped trace. And you can see a 10 to 15 dB difference throughout the spectrum. Note that common mode currents are the dominant cause of radiated emissions, and poor PC board design is usually the root cause. Now that's just the results from a single gap. You can imagine what happens if you have multiple gaps in your return plane. Here are several useful references that include additional information on how signals propagate in PC boards. Ralph Morrison's book, Fast Circuit Boards, is excellent. And there are several others by Dr. Eric Bogatin, the Johnson and Graham High-Speed Digital Design book, and also Schmidt, Electromagnetics Explained, has good explanations of the field point of view. As far as I know, there are only the three of us teaching PC board design from a field's point of view. We all provide public and in-house seminars which cover much more detail than we've been able to touch on today. And we'd invite you to use these references to find out more on this topic.
So the picture on the left is one of my fondest memories. We were finally able to convince Ralph that we should allow him to do a presentation and video this event. And he came to Detroit with Elizabeth, and Ken was one of the participants. And this was our celebration after we had done the videography of this 3-day class. And these sessions are actually available on Ralph's website, which we'll show later on. And then to the right is one of my very happy moments. This is Ralph after he received his Lifetime Achievement Award from NXP, and he's holding his award there. And both of us are very proud. At this point, I feel kind of like the proud papa, because the idea of getting Ralph's teaching into the world sort of fell on my shoulders, and I was extremely happy to get NXP to provide some very visible public recognition for his work. So this is like the fearsome foursome on the left, and I'm with my mentor one of my last times.
Dan, those were such happy occasions for us too. I was really glad that you, after much discussion, really years of discussion, you were able to organize the videotaping of Ralph's work, and that was just great. And also, I was very happy to be at the presentation of his Lifetime Achievement Award. Ralph was so glad for all these opportunities that were provided for him to spread his mission of bringing physics to the electrical engineer.
They were well-deserved moments.
I might add that while I was editor of Interference Technology, we invited Ralph to be the keynote speaker during a series of webinars, and that recorded presentation is on his website right now.
Good.
I want to say to thank you to Elizabeth for sharing Ralph with us.
Yes.
and helping him to continue his career long past anybody else's expectation. So I know that I was really single-handedly responsible for dragging him out of retirement, and it was absolutely worth it to me and to the entire industry. And it's a pleasure and an honor to have been part of your life, Elizabeth, and Ralph's life. And through this, I met Ken and Rick, and the collaboration we've been able to do together has been, like several of us have said, just life-changing.
Yep.
And following these rules on my systems that I design, I have 100% success in compliance. And when I work with my customers and they follow the rules as I try to present to them, they have 100% compliance.
Right.
And it doesn't get any better than that. We continue as a team to prove that physics is real and the rules are very powerful, and circuit-based designs continue to fail. And this is my challenge to the industry. The status quo has become failing EMC.
Right.
And that's not engineering. I have customers who may go 3, 4, 5 different spins on their circuit board before they get compliance. And each time they do the new design, they have absolutely no confidence that they're going to pass.
Right.
And to me, that's not engineering. And the sad part is they're continually willing to pay for these emergency respins of their circuit boards, but they're not willing to pay for their engineers to get the training that would enable them to be successful. So this is the message out there. Stop spending money on failures and spend some time studying the science, and you will be rewarded with higher profit margins. Companies go out of business every week because they can't make their market window, or it's cost them far too much to develop these products. So all I can say is follow Ralph's rules, and it is all about the space.
Yep.
My parents never had an education to any extent, and so I was essentially on my own, and it was up to me to make the connection with the technology, with education, with what was going to happen to me in the future. So I was able to probe, you might say, the environment I had, and to use the interests I had to converse with teachers. And good teachers will take that piece of information and extend it and give you more opportunity. I found that was true in the electric shop, where they made this opportunity for me to run this Tesla coil, or to build a square wave generator, or to do things which were really above and beyond what I was capable of, but they were willing to at least expose me to that real world.
I guess what I want to do is address the idea of power planes as a return. And while a lot of people have preached or actually successfully used this, there are some specifics that are behind that. It's like you only get part of the story. To use power as a return, there are two requirements, and this is both Henry Odd and Dr. Bruce Archambault both will say this in their classes, but a lot of times people miss it. It's if and only if the power plane is only less than 10 mils away from the ground plane, like Ken was saying, 2 or 3 is even better, or the impedance of the power supply is less than 1/10 of an ohm, which requires a massive amount of capacitors. This costs a lot of money, and you still can't route it 3 dielectric layers away. And when the signal changes context, because the energy starts to propagate in the dielectric between the switched conductor and the ground, that is the source where the energy from the power supply comes through, then to change context from the space between the ground and the signal to the signal and the power, it takes time for that conversion to occur. The energy has to couple through the other space. This causes a temporal distortion on the signal, and there's no dedicated space for it to be in, so that signal and all its friends that are making this same transition all share the same space for a bit, and you get crosstalk.
Correct.
The other thing is, when you get to the other side, you have to switch back. So why would I, in my efforts to do a good signal integrity design, a low EMC design, screw my signal up twice?
Yep, I agree with you,
Or
Dan.
spend
You
the
also,
extra
one other
money.
comment, it's important if you are going to reference a power plane for the signal to be, or for the plane to be the same voltage that generated the signal. So a 3.3 volt signal should only reference a 3.3 volt plane.
But even then, you lose signal integrity.
Absolutely. There's no question about it.
Yeah.
But if you reference a 3 volt signal to a 5 volt plane, there is absolutely no path back in through the 3 volt IC that it came from back to the power bus.
Oh yeah, it becomes muddy water.
Oh, it's very muddy water.
There's a couple exceptions, and that is if the signal traces low speed.
Oh yeah.
Yeah, then it's not an issue.
Pseudo
Or
DC,
slow edges.
Yeah, slow
The
edges,
other-
that's the key.
The other exception is some DDR RAM is in fact, some of the signals are referenced to power, but that's
They're not really. That's
No,
the
they're
problem.
not really.
They're not really.
Well,
The memory guys did that because they thought it sounded cool. I'm just going to be blunt and mean.
when you
Okay, if
look
you
at
say so.
the structure, when you look at the structure of the ICs, there's still reference to ground.
Yes, they are.
And that's the problem. And you don't get any of the benefits of differential, because that's what you're talking about, because you don't get any common mode rejection, because
Right.
you don't have, the twisted pair phenomenon. No matter what you do, because they're still single-ended, this trace next to the one on the right is going to affect the trace than the one on the left, more than on the traces on the one on the left, because of the distance. It's a square of the distance rule.
That's right.
And so there's no way you can get any of the benefits, which is why they really don't exist. If you want to do differential like USB or Ethernet or even audio, at the point you get to the driver, you want to eliminate reference to ground, get the ground copper out of there, reference those signals to each other, and stick it onto the cable. But while it's on a circuit board, you can't change it. Unless you've got an actual inverting power supply, you're still using power that came from the same dielectric with a plus and a return.
That is
And
correct.
one side is inverting and one side is non-inverting. And even, Lee Ritchie's gotten several papers now that show you that that's how things behave. Dr.
Right.
Hubing has got papers that show this is true.
Right.
So it's just a matter of trusting the geometries and trusting where, the whole idea is you have to be able to see an unbroken dielectric from the switch to the load with an unbroken return conductor or ground, and then the switch conductor. If you can't see that dielectric intact, then you don't have a way to move the energy from where you have it to where you want it without causing some sort of distortion.
I wonder if we could start answering some of the Q&A questions. It looks
Good
like
idea.
there's 14 of them so far. We
Good-
don't want
good
to
idea.
run this too long.
Go ahead and read them, somebody.
Can you just click on your Q&A and you'll see the list.
Oh, okay. Sorry. Where
It's
is
at the
it?
bottom of the screen.
We could start at the last one and move backwards.
Okay.
That might be easier. 4-layer stack-up signal power ground. I don't understand the stack-up signal power ground. Both of those, you've got ground layers next to stuff.
Yeah.
And so you've got a good transmission line. The only thing about a 4-layer stack-up is most people can't afford to have 2 ground planes. So what I see typically in automotive is we do a signal ground signal, and then layer 4 has to be routed as if it was a single layer board. So every signal needs to have a coplanar ground copper next to it. And then when you move from layer 4 to either 3 or 1, you absolutely have to have a ground transition via to connect that horizontal copper on layer 4 to the horizontal copper on layer 2 so that you have continuous dielectrics. Yes. From an EMC standpoint, honestly, both of those stack-ups are going to be roughly the same. The only advantage to the second one is all of the open space around the signals could be made power, which would probably have the effect of lowering the power bus impedance, which would then in turn give better performance than the top 4-layer stack-up. So if I were going to use one of those two, it would be the second one. But I agree with Dan. It's seldom that you get to put 2 ground planes in the middle of a board. I've done it, but it's rare. Especially a 4-layer. And in the 4-layer board, you're not going to be running a beast BGA at a gigahertz. So you're not looking at any high capacity dielectrics either. Right. I mean, people who need very high impedances. Yeah. Yeah, people who need to run processors and FPGAs at gigahertz speed shouldn't be using 4-layer boards. Sorry. Yeah, that's a challenge that's coming at everybody because the traditional, quarter micron, 8-bit microcontrollers are being replaced by, ARM-based supercomputers that are in, little tiny packages that you can buy for 50 cents, but they're in, 55 nanometers. So try to throw those on a 4-layer board, you're going to have a real challenge just designing a good power distribution system to feed that beast, because it's still switching in 100 picoseconds or even faster in the
Right.
core.
It's crazy. Let's go to the next question up. There's a lot of talk about slow speed, high speed, supers, high speed impacting the rules on what order is each one. Oh, you're talking about frequencies. It isn't about clock frequency, it's about rise time.
Yep. I follow the
Clock.
rules no matter what switching speed, period.
Right. That's absolutely right. Yeah, I treat even low speed boards with care if I can, but I treat high speed. And when again, it's about edge rate, it's about rise and fall time, not clock frequency. And once rise time gets faster than a couple nanoseconds, if you're not taking care of things, you're in trouble.
Okay, voltage matter for high-speed AC return current. The key is you have to have designed the low impedance return path.
That's
If you
correct.
haven't created a dielectric that matches the switching speed of the driver and the distance between the driver and the receiver, then you're going to have problems with crosstalk and radiated emissions.
Somebody asked a question here. Describe the transition from circuit traces to antennas or waveguides. A circuit trace above a plane is a waveguide.
Yes, just a real crappy one.
Period. And to an antenna, it would be the same thing. I mean, basically, you're creating a trace above a plane, which is a waveguide, and you can feed an antenna with that.
And the higher impedance of the transmission line, the more likely you're going to have energy that will escape, because the closer you get to the 377 ohms of free space,
Right.
the more energy is going to couple into that free space, and it never comes back.
Guys, there's some that are asking to repeat the question before the answer.
Sorry. Good point. If I'm driving a patch antenna with a microstrip and ground, a microstrip means a signal and ground, by the way, and I remove, where the hell to go? Oh, sorry.
There's more questions coming in than we can answer.
Before the patch edge, will the patch still receive power? Well, yeah, it will, but the fields will spread out before they get to the patch edge. So you shouldn't remove the ground before the patch edge. Would you guys agree? You see the question, Dan and Ken?
I'm looking at it.
Well, I think they're just wondering whether they should put a void area
In the ground.
around that patch antenna in the return plane.
And the answer would probably be yes, around the patch antenna.
Yeah.
But the trace feeding the antenna still needs to have return all the way up to the antenna.
Correct.
Yeah, at the point where you want to start the energy to move from the space between the trace and the ground to the antenna into the outside world, that's where you want to remove the ground so you couple as much energy as possible into the radiating structure.
Right.
The one for high-speed SOCs, I don't know what operating frequency does internal trace length. It's really, again, not the frequency of the device. You can run it at one kilohertz. Every time the clock switches in one of these beasts, it's going to be about 65 or 70 picosecond for the core. And then looking at the different buses, things are going to switch. DDR4 switches in 72 picoseconds or 12.2 gigahertz.
Right.
So this is where not only does the impedance matching device have to be on the IC, but you immediately have to catch that energy onto a controlled impedance structure on your printed circuit board. So there's just no way of matching impedance with these higher speed devices. So it's, again, you need to find, hopefully it's in the IBIS model, the switching speed of the driver that you're using. And for typically, even at a nanosecond, you only get about an inch for before you need to have a controlled impedance transmission line.
So somebody needs to mute their mic.
Yeah, it's not coming from here. I'm not sure.
I like this one. What about removing ground plane under an SMPS inductor? This is a wonderful question.
Yes, it is.
On the layer where any series component, a resistor, an inductor, you want to remove the copper underneath it, because your return, you have to pretend it was a trace before it was a component. So its return is going to be in the next layer, ground plane. So absolutely, you want to pull the copper from underneath it, because you want that field between the conductors in the inductor to be in the space between that and the ground plane underneath.
But if you do put ground copper under the inductor, then you need to have vias connecting it to the ground plane on 2, so the fields can get up to that space between the inductor and the top ground copper.
Well, you want to deliver power to the inductor, from the driver,
yes,
with a continuous dielectric.
Now, are you guys which layer are we taking the return plane away?
Well, no, underneath, on the same layer as the component.
On the same layer as the component.
Yeah.
Gotcha.
I've done a lot of experiments with exactly this, and we've measured the difference in the behaviors.
If you don't have copper port on layer 1, you're routing to an inductor through it and then beyond, then you absolutely never break the ground plane under it.
Okay, I wanted to clarify that, because it sounds like the question is asking whether to remove the return plane under the inductor, and that is not something you want to do.
Absolutely no, never.
Yeah. Okay.
Well, I never use coplanar copper for the return on a SMPS.
Okay.
I use the adjacent planar copper.
What he's saying, if there's a ground plane on layer 2,
no, he's talking about underneath
ground under the inductor, and the answer is no.
On layer 1.
No, layer 2. Forget layer 1.
Right,
Assume there's no copper pore on layer 1. Right. If the only ground plane is layer 2 and you have an inductor, never open the ground plane under that inductor.
Oh no, you use that. But what he's asking is about on the layer where you've mounted the conductor.
What about mounted the ground? It doesn't say that. It says.
Well, it's not clear, Dan.
Okay,
it's not clear.
A lot of people will flood underneath series components, and that's a bad thing.
I agree with you. It certainly can be, unless the component's big enough that you can add vias to be able to pull the fields to the surface.
Oh yeah.
Right? You agree with that?
Yeah, no, that's good. Yep.
As far as ground flood or ground fill, I'm against that, but that's maybe another debate for another time.
Yes. Well, the only downside to not having it, the benefit of it, even if it doesn't benefit the circuit performance, is it does make the board easier to fabricate.
Well, let's move on.
There's better ones. As you can see, there's a lot of religion and passion in all of this.
On your recommended 8-layer stack-ups, where should the high-speed signals be routed? 133 megahertz clock, 25 megahertz clocks. Again, it's not about clock frequency. It's about edge rate.
We have not enough information there.
How fast is the edges? How fast are the edges of the signal? And the truth is, you can route high-speed signals on the top layer as well as you can inner layer, except the fields won't be as well contained. That's the only downside to top layer routing.
As long as there's an adjacent return plane, it doesn't really matter that much what layer you route them.
I agree with that. If layer 2 is a ground, then even layer 1 is an adequate place to route stuff. What I never do on the outer 2 layers of a board is put 2 signal layers above a plane. Now, see, I don't have the situation Dan does with the automotive world, where they're forced to put one ground plane in a 4-layer board. The boards I design, we never put signal, and then a ground plane, because you're asking to create common mode currents between those two signal layers, because their fields are going to blend in the dielectric space between 2 and 3. And that will create common mode energy. Okay, what else do we have here? What about gaps in ground planes as, a slot antenna? If your goal is to create an antenna, yes, then a slot in a ground plane is what you want to use. There are people who will put slots in ground planes and then route a trace over them because they wish to radiate energy. If that's your goal, yeah, slot antenna can be made that way. But what Ken was trying to tell people is don't do that if your goal isn't to cause radiation. Agreed, Ken?
Agreed.
How much does it matter if the paths are extremely short? How much does what matter? You mean all the things we've talked about, or the slot antenna, or what?
It just
Less than
depends
2
on the switching
millimeters
speed of the
between
transistors.
power source and device, but no way to have a good return plane.
I think the question really is length of the signal trace.
Right.
How important is it to have a return plane, maybe?
Even with, well,
I guess it depends.
Yeah.
It depends.
Yeah, with 2 millimeter traces, that's only an 80 mil long trace. It's not critical because it's a lumped element at almost all speeds.
Good answer.
Some of these questions are pretty heavy and would take a lot more time to discuss, I think.
No traces over gaps in layer 3 below the inductor cutout. Why would you put a cutout in the inductor, Gordon? Under the inductor. Don't do that. 2-layer misery. Ah, okay. If it's a 2-layer board, well, it says layer 3. I'm sorry,
Not
Gordon,
sure it's a
I'm
question.
confused about your question.
Yeah, I'm not sure it's a question. Let's move on.
You shouldn't put traces over gaps. That's a fact. Hatch ground for Gordon said hatch ground for capacitive touch sensitive areas. Ah, I assume the hole size sets the problem area frequency. Smaller holes, higher frequency before problems happen. Yes, when you need to have a crosshatched ground, when I worked for L3, we used to, when we had flex boards that had to be dynamically flexed, meaning during operation, we would use crosshatched planes. We would still do controlled impedance, and as long as the hole size in the hatch is way smaller, is a lumped element at your highest frequency of concern, then it's a non-issue. You guys agree with that? Ken, Dan? You understand what I was saying?
Yeah, I think so.
If you route a trace across a crosshatched plane and the size of the holes in the hatch are way smaller than the smallest size that creates a lumped element, then it's a non-issue. It's not.
It should be, yeah, it should be invisible if it's so small.
If it's a lumped element, it's invisible.
You don't get any reflections. It's all that, as long as you don't get the second order reflection, you're okay.
That's right.
You know,
I guess I'm not that familiar with capacitive touch sensitive areas, so I'm
well,
going to
this is it's just a basic idea of as you
Of
come and
using
go.
a crosshatched plane.
Yeah.
Okay.
Yeah, we used to use them all the time. You just have to be careful not to let the holes in the crosshatch become large enough to become a distributed element. Does that make sense?
I've got a suggestion. Can we start at the top of the list? Because those are the older questions, and I think the people that ask those deserve to get an answer before they
Yes.
have to go.
I agree. The question, for which edge rate versus length of the trace would you start taking precautions? There's a rule of thumb that Dr. Eric Bogatin uses that's easy to remember. If the trace is longer in inches than the signal rise time in nanoseconds, you need to pay attention. And that's actually a conservative statement, but it's a good rule of thumb if you really want to take a cautious approach. If the trace is longer in inches than the rise time in nanoseconds, you need to pay attention. So a 1 nanosecond device, a trace longer than an inch, you need to take care of it. A half nanosecond device, trace longer than a half inch, you need to pay attention. And so on.
Yep. Then you have to match impedance and drive.
Then you have to
control
match, that's right.
impedance.
You have to match impedance. You have to be really cautious about changing layers. You have to think about all of that stuff. At 10 gigahertz, is it my understanding that routing on the top layer increases dispersion? Yes, it does, because not the same impedance on the top and bottom of the trace. It's not about impedance. It's about the dielectric constant of air versus the decay of the board material. So the amount of energy that's above the trace will be traveling at a higher speed than the energy below the trace. And that fact causes signal dispersion. Most people ignore signal dispersion because in most digital systems, who cares? But at 10 gigahertz and beyond, yeah, it can become an issue. And the boards in my life I've designed that were 10 gigahertz, 10 gigabits and up, we have paid close attention to that and done most of the routing on inner layers for exactly that reason. Signal dispersion is a problem usually in the analog world where you're talking about RF frequencies above 5 to 10 gigahertz. That's where it can get ugly. What's the best way? Oh, go ahead.
Rick, there's a question for you. It's actually the very first question of the Q&A. It's asking, on your 6-layer stack up with multi-power polygon, what's the spacing between signal and power polygon? It's at the
I'm
top.
sorry, where is it? Is it on the Q&A?
Yeah. Look at the very top. You have to scroll up there.
I am up there. All I see is recommendations on layout structures to get power from inner layer. Is it in the chat panel or the Q&A?
It's Q&A right at the top.
Oh, but maybe it's because you joined later, so maybe you cannot access it.
It could be that I can't see it. Can somebody read the question to me and then
Sure.
I'll try to answer it.
Yeah, okay. The question is, on Rick's 6-layer stack up with multi-power polygon, what's the spacing between the signal and power polygon?
That's a good question. A question I often ask in classes that I do, because sometimes we'll pour ground on signal layers, and most of the time we're pouring, oh, I see the question now. Most of the time we are pouring power. When I pour ground, I sometimes allow it to get close to the signals, and meaning we allow it to have an impact on impedance. Because you are adding coplanar ground copper in addition to the ground copper under it. When you're talking about power, you generally don't want it to get real close. And if you want to keep it far enough away that it doesn't impact impedance, or that the power fields and the signal fields don't couple tightly or at all into each other, we generally keep the copper 2 times the dielectric spacing away, keep the copper 2 times the dielectric spacing away from the signal. So for example, if you have a circuit board with dielectric spacing of 6 mils, I will try to keep the power pores 12 mils or more away from the signal traces. So
Yep.
they don't, so the fields don't impact each other.
Of course, it's going to be significantly less because you're looking at the edge of the copper foil as opposed to
That's right.
the bottom surface or top surface of the copper.
Yes, that's correct. The top surface has a minor impact near the edge, but it's mostly the edge, you're right.
Let's move on to Patrick's question here. Everybody see that one? It's
What is it?
rather lengthy.
What? I don't see it.
It's at the top of the list again.
These must be coming in late to me because
Well, if you go to the top,
I am at the top.
and it's the first one in the top.
The top one that I see says recommendation on layout structures to get power.
Are
Is
you
that
in the
the one?
open one? Open one?
I'm sorry.
On the question and answer?
Yeah, I'm on the Q&A panel right now.
Yeah, Rick actually joined later, so I guess the first questions are not.
Oh, he may not see the question. Okay.
Yeah, I did sign in late.
Ah, okay.
So what's the question?
Let's see. Let me get down to it. Can you please comment on 6-layer designs / stack-ups where there is one thick core in the middle rather than 2 cores? All the examples shown are a stack in which you have 3 sets of 2 layers. I'm assuming he means 2-layer cores. What about 2 sets of 3-layer? For example, one thick core between layer 3 and 4.
So the only way you can get that is in an HDI board. If you buy a standard circuit board and don't tell the fabricator how to stack the board, they will put 2 cores, one of them between 2 and 3, and the other one between 4 and 5. That is how circuit boards are fabricated. If you want a thick core in the center, you could ask for it, but it would change the way they build the board, and they would have to core laminate, and you'd be paying for an 8 or 10 layer board if you do that. Or if it's an HDI board, you would have a thick core. First off, thank you for doing this. Oh, it's
Oh, you're seeing it now.
Oh, I am seeing it now. Somehow it popped in, but just now. I'm reading fast circuit boards currently, and I'm learning a lot. Appreciate all your rather than 2 cores. Let me read that again, make sure I understand it. 6-layer design stack up. Rather than 2 cores, all the examples shown are a stack in which you have 3 sets of 2 layers. That's not how circuit boards are fabricated. If you're reading fast circuit boards and that's how the boards are shown, that's incorrect. Circuit boards are not fabricated. The top dielectric of a circuit board is always a prepreg, always. It's never a core, then prepreg, then core, and so on. Now you can get them made that way, but they will cost you extra. So if you buy a 6-layer board, for example, that's core laminated, you'll pay for 8 layers. If you buy an 8-layer board that's core laminated, you'll pay for 10 layers. And that's why fabricators foil laminate, because there's less processing time and fewer materials necessary to build the board. And mainly it's about processing time and chemistry. So when you build a 6-layer board with 2 cores, 2 to 3 and 4 to 5, you're paying less than if you had core, prepreg, core, prepreg, core. So that book on fast circuit boards, that's probably a mistake in the drawings or a misunderstanding.
Yeah, Ralph was more about trying to describe the physics than he never built any multiple layer boards like these.
Yeah, oh, you're talking about his latest book then?
Well, this is fast circuit board, so the one before.
The one before, okay, yes, I've read that, and yes, I was going to say something to Ralph. Those were in the wrong order, but oh well.
Let's move on.
Yep. Read the next one. I'm not sure I have it.
How much connection is needed between the ground planes, especially at microwave frequencies?
I think
I'm
what he wants to know
assuming
is how
he's
many vias, and the answer
referring
is
to
what's the
vias,
frequency.
stitching vias.
Stitching vias have to be they have to be close enough together that the distance between them is a 10th wavelength in decay of the maximum frequency. So
Or
for
less.
example, if your maximum frequency, let's say rise time frequency, if it's a digital circuit where your rise time frequency is a gigahertz, then a gigahertz in decay, the wavelength would be 6 inches in an FR4 board, and a 10th of that would be 60 mils. So the vias need to be at least no more than 600 mils apart if the top frequency is a gigahertz. If the top frequency is 10 gigahertz, then the vias need to be within 60 mils of one another.
Okay. So next question, can you explain how the common mode currents are generated from adding the gap in the return plane, I assume?
Yes, why don't you handle that, Ken? I thought you did
Yeah.
a good job in that.
You know, I've tried to explain that a number of different ways.
So have
And I've reached out to Dr. Bogatin and also Todd Hubing on that. And, you know, I'm not sure of the physics on that, but it does happen. I think I might refer that question to Dr. Hubing or Dr. Bogatin, who are both listening to this, I hope still. And maybe they can answer that in you know, a blog or something.
That would be
Well,
wonderful.
a lot of it's because it pushes the field. It has to go find the other edge of the ground copper. So it goes from happily going between the trace and the ground plane underneath it to finding a big hole that it has to fill. So it has to find the edge and fill that entire space. So that energy moving into that space is going to have more density between it and the next trace over horizontally because they're closer together now. The field moves over to there. So you've actually gone from having a trace that's an inch apart, for example, to where the gap is only a quarter of an inch or a half an inch away from the next trace. Then you've reduced that space, and it's about the square of the distance again. You reduce the distance by, you know, X, then you're going to have 4 times more energy coupled.
So it's
Yeah.
about the coupling of fields.
Yeah,
Yep.
exactly. Yeah, there's a mutual coupling factor that,
and that's what induces the
enters
common
in.
mode current in the other
Yeah.
transmission line.
So crosstalk would be an event that would not only potentially cause signal integrity, but would induce common mode currents.
Yes. I think you've got some good slides about that.
Yes, and that's pretty much how I describe it, is what you just talked about. But I would like to hear Eric and Todd's answers to that, because I respect those two a great deal and love to hear their answers.
Yeah. It's all about a mode conversion happening.
Yes,
From
that's exactly what it is.
differential to common mode, and any kind of upsets in the geometry of your board are going to create those conversions from differential mode to common mode, and that's
every physical change. That's a good point, Ken, because every time the geometry changes of this transmission line or the space, there's going to be a reflection. And the hope is that the reflection is not at such a magnitude that it affects the signal. And that's the problem we have to face and have to address when we design these circuits. That's where you hope you can stay at that magic lump distance so that all of the reflections are buried in the incident wave as it continues to move forward into the transmission line.
okay. Let's keep moving.
Yep.
So the next question is any opinion of Henry Ott material. I think we need to be very respective. I think most of the material in his books is very accurate.
Oh, I agree.
And having said that, I think our understanding
What's the
as
question?
far
I'm
as
not sure I can see it.
as far as field theory, how fields act, is probably not been addressed in anyone's book except Ralph's most recent one. And so I think you can trust Henry Ott's books, but you know the science keeps evolving. I guess that would be one way to put it.
The big thing everybody has to remember is the context in which the material was created and the technology that they were using at the time. Howard and Henry and Lee and all these guys, they're telling you things they did that were very successful in the industry during the technologies they were involved in. And from their experience, they came up with some rules. The rules in a lot of the cases were absolutely correct. The rules in other cases were what I call, they just weren't so wrong that they caused failures, again, at the technology levels that they're dealing with. We're into the nano world where typical signals are switching in a nanosecond or faster. So suddenly things that were benign become an issue. And that's where we've had to rethink our design guidelines, because as we are faced with these faster and faster geometries, you know, like right now we're going to 14 nanometers in some of our devices at NXP. There are 2 nanometer working devices out there. All of these things present very, very difficult problems to solve if you aren't exactly following the rules of physics. We got away with it in the past without following them, and everything seemed to be okay. I mean, that was my happy world in TTL days.
I think if you ask, I think if you ask Dr. Hubing, he's got some commentary on his website, learnemc.com, I believe it is.
It is
on design rules, and so many of the design rules that were developed, you know, 1 or 2 decades ago, or even 5 years ago, may not apply to designs that we're doing today. And so you have to be very leery of any kind of design rules. They may have worked for a particular application, but they may not work for your application, I think is probably an important point to keep in mind.
That is a good point. That's why I try really hard to get people to understand why things happen as opposed to what to do. And I try to preach that, and I know you guys do too.
Let's go on to the next question. Okay, the question from John is, at some point I need to better understand the different types of dielectrics and used on the boards and the limitations of each. I think that kind of goes beyond the discussion today. That might be best asked to somebody like Lee Ritchie or some of the others who are really into the high-speed design.
Right.
Well, the issue with the prepreg isn't so much that it doesn't hold impedance well. It's much more difficult to hold a uniform structure.
Uniform thickness.
Yeah, because as it goes through the lamination process and you throw a copper foil on the outside, we don't have the technology to press everything down and end up with the same, you know, thickness across the entire structure. And that, coupled with the fact that the glass isn't uniform throughout the board either, that you end up with minor discontinuities. And for most circuits or systems, it isn't an issue. And in fact, my belief is that if you have a problem with signal integrity that are driven by the glass mixture or the way the prepreg thickness is held, you need to use a different material at that point. You need to go to some higher performance Teflon or something with a different physical property where you can get a more uniform structural, and then you can count on what happens as the waves move through there. Because remember, the electromagnetic fields don't go through molecules, they go around them. Right. And as the molecular density changes in the mixture of the plastic and the glass, the time it takes for the field to move through that space changes. And that's what gives you some differences. And if it's a signal that this affects it, you should be using Rogers or some other type of material.
If it's a high enough speed signal, that's correct.
Yeah,
and then,
yeah. And that's
right.
it. That's it. Something, I mean, like Rick and I were both doing 12, we're doing DDR4, DDR LP, everything, which is, 12 gigahertz and up without a problem, without using any exotic materials.
Right.
But when you start looking at the radar stuff and some of the other very high speed signals that are starting to be used, then you have to start looking at doing either integrated layers of a different material, right, or daughter cards where you do it on that special material. I think a lot of people right now are going to module design, especially with the Wi-Fi's, the Bluetooth, the NFC stuff, because you really need to have a different material for that particular piece of the circuit, and it's not cost effective to pay that penalty on the rest of the board.
Right. Yep, I agree. We used to mix very high-speed analog stuff with digital on circuit boards at L3, and we would typically put the exotic materials on the outer layers and put all the high-speed stuff as microstrip circuits on the outer layers, and then have the whole inner part of the board be FR4, and all the digital circuitry was in the board in FR4, so that we didn't pay the cost penalty through the entire board. It's an easy way to accomplish that.
Yeah, but even across the whole board geometry now, it's difficult to be competitive.
No, I agree.
Without using a separate module. SOCs are going to become a lot of the norm now.
Yeah, I would think so.
Like we're moving into that business pretty heavily, I think, because it's such a challenge to do both the design and the manufacturing of these very high speed signal based assemblies.
Well, moving from high speed to high voltage, there's a couple questions here. I'm not sure I have the background to answer, but the question is, I design in high voltage, high-ish speed PC boards. We're talking 1200 volt DC with rise times of 700 to 800 nanoseconds. And then his real question is, how would I handle issues of minimizing gap thickness if I can't thin the dielectric and I can't run a ground return plane along the bottom?
Well, that's a good question. Unfortunately,
you have to have the dielectric thickness to keep from starting fires.
Right.
And I'm actually working on some similar stuff because my son is doing battery management systems for his company.
The reality is FR4 has a dielectric withstand of 1,000 volts per mil. So in terms of thickness, you don't need a lot of dielectric thickness to avoid punch through. It's spacing on the surface that needs to be high.
The coplanar, yeah.
Coplanar spacing needs to be high to avoid arcing. And in terms of speed, when you were talking about 700-800 nanosecond rise times, unless he meant picoseconds, I think he said nanoseconds, that's not high-ish speed, that's very slow.
But at 1200 volts,
I know, it's a lot.
I don't know if that's a DVDT or DIDT we're looking at.
That's
right.
definitely
I know.
DVDT.
The slew rate is still fairly fast.
Yeah, that's DVDT.
You take 800 nanoseconds and divide it by 1200.
Yeah, that's a good point. Yeah, that's a good point. Yeah, I guess it is high-ish speed. The slew rate is still fast.
It's a real challenge, and a lot of people are still trying to figure out how this how to work on this.
The real challenge is the coplanar spacing.
It makes you have a lot of problems if you want to make a smaller geometry PCB. I mean, there are UL requirements that require you to have a much larger PCB than you would like to have because of that.
Right.
Let's do a time check. Lucy, how long do you want to keep this going? We still have 15 open questions.
Well, you can go as long as you want, but another option would be that I could email you these questions and maybe you can answer by email later if you guys have to go.
I don't have to go. I have no place to be.
Yeah, I'm okay.
Great.
Let's
Okay.
keep reading.
Just wanted to make sure. So Richard is asking if trace width is reduced to unit width or zero width, does the field theory hold?
How can trace
Well,
width be reduced?
if you have a zero width trace, then you don't have a transmission line.
That's correct.
The field is in the space. So if
Yeah.
you go from 10 mils to 0 and the energy is in that space moving forward, because it has to be moving, then it will be delivered to space. That's how
It's going to radiate.
radio works.
That's right.
That's exactly how radio works.
Right.
Yeah.
So it just radiates.
Right.
And the efficiency of that coupling into free space is determined by the switching frequency and the length of that conductor.
Right.
As you get closer to a quarter wavelength, you have maximum coupling.
Correct.
Okay. Next question is, I don't really see a question here from Fazlul. Less than 1 nanosecond rise and fall times. Maybe the question is that an issue? And I would say yes, it would be. The faster the rise and fall, the more harmonic content you're going to get in your digital signal.
Right.
And the more chances that it's going to couple and radiate out.
It requires that you use a transmission line, and depending on the distance between the transmitter and the receiver, you may need to do some type of impedance matching and then route a controlled impedance transmission line for the rest of the distance.
Right.
LCD displays are notoriously horrible.
Yes, they
because
are.
most of them have such crappy state machines that you need a nanosecond event going into them, or the state machine loses its mind. But they're not routed, they're not built so that you have a transmission line. So you can do a wonderful job going from your driver to the cable, and then you have this open network that's, basically a high impedance disaster.
The cables are some of the worst I've ever seen.
And the pinout for the LCDs are not such that you get transmission lines.
LCDs put a lot of food on my table.
Oh, I'll bet they do.
Yep.
Yep.
And just for the reasons you suggested, the pinout is awful. You've got a whole bunch of signal lines with maybe, if you're lucky, just 1 or 2 return lines.
So the grounds are on the outside.
Yeah.
Yes, they are. Yeah.
Where they need to be a whole second flexible, it needs to be a rigid flex with a ground plane.
Right.
Or they
James,
need to fix their state machines. So go ahead.
Next question. James is asking for a recommendation on layout structures to get power from inner layer to single pin component on an external layer.
Got to have a ground transition via next to your power via, and you can't route anything between it. It's a Z-axis transmission line.
That's correct.
You got to connect the dielectrics.
Yeah, people tend to think in terms of moving current, but it's about moving fields.
To keep that field energy trapped, you need 2 pieces of metal, as Ralph will say in his book.
With nothing between them.
Those 2 pieces of metal have to be continuous.
Yep.
Okay. Next question. Javier is asking, what is your opinion about connecting ground return plane with chassis reference at connector level? And Yes, that you know, if you do have to go to chassis, and for automotive applications, certainly the car body would be your chassis reference or the ground structure. So yes, you want to have a high frequency connection between your I/O connector, connecting the digital return to chassis.
That is generally what's done in that situation. When I was in both telecom and avionics, we had just the opposite scenario. We couldn't attach our internal ground to the chassis because it created other problems. In telecom, it was done for safety, for safety reasons, according to the NEBS and Telcordia requirements. And in avionics, we had such high levels of lightning to pass that whenever we attached one to the other, we ended up usually with problems. And so we kept them isolated and would have a chassis plane near the connector, but we would generally bridge across to that with transformers or some other method to get signals to reference that instead of the ground to go out through the connector into the shield or whatever the case may be.
Ethernet's a good example because a lot of times people use a capacitor to take the connector ground shield to the system ground.
Yep.
Or sometimes I've seen where you have a copper structure that's connected to the shield that's just over top of the ground plane, and you use the
dielectric
capacitor
to make the capacitor.
Yeah. Todd has talked about using that.
Right, I've seen that done before as well.
Generally, you do not want to run return currents through your chassis structure, though, or your.
Oh, you don't want any, because that's where you get your worst case radiated emissions.
Right.
That's what Ralph's got 10 books about.
Okay, let's move on to the next one. Say, what's the best way to increase speed on a single layer board? I have 1 megahertz, 1200 volt DC switches that so far all I can do is minimize the trace length on these.
Well, your clock is 1 megahertz, but you're switching at something significantly faster, I'm sure.
But if you want to, when you say increase speed, does he mean the speed of the signal moving through the board?
Probably the clock rate.
Yeah,
because to increase efficiency, you want to increase the number of times you're turning on and off the source of energy.
Right.
Well, if it's a single layer board, isn't this where you would go to your triplets?
Well, it'd be signal, ground, signal. Yeah, you would have to make sure that everything has a signal trace next to it. This is where my
return trace, you mean,
thickness makes nothing changes, because now your impedance of your transmission lines is determined by the edge of the foil. So you might need 2-ounce copper in order to get some reasonable coupling. But doing any kind of high performance system on one layer is really not practical anymore. You're going to have problems you're going to have problems passing any type of EMC, and the spacing is going to give you a huge challenge on your UL and the cost. You're going to do a lot better going to a 2 or 4 layer board and reducing the physical geometry of it and use double-sided assembly, and then use those 3 dielectrics that you have in a case of a 4 layer board to move the energy. Because if you've got 3 5-gallon per minute pipes, now you've got 15 gallons per minute. If you've got coplanar copper, you've got 1 gallon per minute and you need 5. Well, you can't get that. You're going to burn the traces off the board, which is why people fall back to going to thicker copper, because they think that reduces the impedance, but it just
doesn't.
Reduces the resistance, but you still end up with a lot more of the energy being converted into kinetic energy, and that just means that you can get hotter before the traces curl up off the board again.
Right.
Okay, let's go on. So Enrico is asking, what's your go-to field solver?
For me, it's I've used several. The one I like most is the Polar SI 9000. I've also used the field solver from Hyperlinks and the one in Altium 20. I've used all of those. I've used a number of others as well, but my favorite's the Polar SI 9000. It's not cheap.
Yeah, I think you have to be careful with simulations, with the exception of the ones that Rick has mentioned. Those are designed specifically for PC board design. But simulators in general, they're good for evaluating interconnects,
Right.
but for whole boards, probably not.
And they're good if you're almost perfect, if you're almost already good.
Yeah.
If you're not, they aren't doing FEA analysis.
Right.
You know, so they're not looking at the dielectrics or the three-dimensional structure. They're RLC models still.
Yeah.
So I don't use field solvers. What I do is just use the rules that are geometry based. I have a series of tables that tell me, you know, if this is the switching speed of the transistor, what is lump distance for that? And it tells me whether or not then I can see how far apart are my driver and receiver. I know whether I need to have a controlled impedance transmission line. Then I just design it that way.
Right. Well,
And
that's why you
magic
use the
happens.
field solver, though, Dan, is to figure out what trace width and dielectric thickness you're going to need to get the impedance you want. That's where field solvers are handy. Let me put it that way.
Yeah. Yeah, I just be careful how.
But you can go into just any run-of-the-mill, you know, how wide is your trace and how thick is the dielectric. It'll tell you what the impedance is, because you don't have to be exact.
Can use a
Well,
spreadsheet
I
for that.
disagree with you there. You know, the statement was made earlier about the impact that prepregs have on impedance. And because of that and other variables, etch factor and other things, fab houses now will only promise you plus or minus 10% control of impedance. And that's if you send them a design that's almost spot on. If you send them a design that doesn't really match the parameters to give you plus or minus 10%, they're going to, you'll be getting a call or an email that says, by the way, we're going to have to change your design. And I've seen a lot of people get that email.
Okay.
So you got to be careful is the point.
Fazlul is asking, if you have multiple ground return planes, you can stitch them together at the periphery of the board and keep the high-speed signals on the internal layers caged, correct?
Well, yeah, that's basically true because you're forming a z-axis connection that in effect closes the wall.
Yeah. Yeah, that's effective
really,
in some cases.
There's really, other than the power planes where energy can spread, there's really no need, quote unquote, to keep them caged. The signals will, if you're routing signals of one layer away from a plane, the fields are only going to spread so far before they couple to the plane anyway. So as long as you're away from the edge far enough to prevent that from coupling off the edge, you're fine. But yes,
yeah, good point.
Yes, to answer the question, the vias will do that.
Yep. Next question from Leonard. Can you speak some on recommended grounding techniques for cable shields?
First off, I got to hit that. And I know you're going to say the same thing, Ken. You don't ground cable shields. You attach the cable shield to the chassis. It is a continuation of the Faraday cage.
That's if you have a shielded enclosure.
Yes, if you have a shielded, if you don't have a shielded enclosure, what good is a shield? Because you can't continue the Faraday cage if you don't have it. Think about that. I know people do it, but I've seen people get into trouble trying. Anyway.
Well, if you don't have an enclosure, you need, there's a couple things you need to do, and for a lot of mobile and portable products, they don't have shielded enclosures, nor do, for example, automotive modules. But so the two things you want to do is each pin of the I/O connector, you need a capacitor to the digital return. And the other thing is you use common mode chokes.
Right. What do you mean by a capacitor to the digital return? You mean from each signal pin?
Each signal pin needs a capacitor to the digital return, and that's the other thing you can do. There are some cases where you may need to have a partial shield either on top or underneath the board, and so the each side of that shield needs to be connected to digital return to confine any common mode currents that tend to get out on the cable. It
Oh, I
just
see what
provides
you're
an
saying.
alternative path back to the source.
Right. I see what you're saying. Right.
Yeah. So, you know, if you have a product, and so many of them do not have shielded enclosures, it presents extra challenges for the designer.
That's a fact.
Jim is asking, what is a cross-hatched plane?
It's just
And
what the name
why
implies.
would you use it?
It's a plane with holes in it so that it looks like a bunch of lines routed next to one another, and then 90 degrees from those, another bunch of lines routed next to each other. So instead of having solid copper, you have copper with little square holes in it that cause it to look like a pie crust on the top of a pie where you've used strips of dough rather than a solid dough on top of the pie.
And why would you use that?
Why would you use that? Mainly, people use that in the flex world where they have a dynamic flex board that has to actively flex constantly during service. You have some moving head that has electronics in it that attach to a box at the end of a channel, and this head moves back and forth, and there's a flex cable between the electronics at the end of the channel and the moving head, and that flex cable is constantly in motion. If you put solid ground planes in flex boards like that, you wear them out and they eventually fatigue and break. And crosshatch planes are much more prone to hold up without the fatiguing and breaking. And when you use a crosshatch plane, it will change the impedance of your traces. And one of the advantages of the Polar SI 9000 field solver, it allows you to simulate impedance control with a crosshatch plane as well as a solid plane.
You want to make sure the holes are like a tenth of a wavelength.
That's
at
right.
The highest frequency of concern.
That's
or something
exactly
like
right.
that.
That question was asked earlier. Do the holes in a crosshatch plane cause a problem? And the answer was only if they exceed a 10th wavelength of the highest frequency, meaning the highest rise time frequency.
Okay. Brandon is asking, should fast rise time signals, for example, DDR3, be routed on external layers or inner layers where layer 2 is the return plane? The goal is to limit emissions and signal integrity issues.
I know the answer, but go ahead. One of you say it. Personally,
yes.
yes, that's good.
If you can.
Right. The reality is fields are better contained on inner layers.
Yep.
But from an EMI standpoint, differential mode energy referencing a plane on layer 2 won't cause EMI problems even if a signal is routed on layer 1. Yes, the fields aren't as well contained, but unless the fields that do come off the surface are able to couple into something which can resonate and radiate, they're not going to cause an EMI problem anyway.
Yeah, the biggest issue are going to be timing.
Yes, it's timing. That's right. Outer layer signals travel faster. And what speed do you need for the signals to be moving? That's an issue.
And what's the requirement for the length matching?
That's correct.
You know, what's the state machine need? And this is another one of my hot buttons.
Oh, you and me both.
Rick is good. The doggone app notes for the memory vendors, and from us too, are so conservative that they cost people layers. You know,
Right.
it's money out of people's pockets. And when I asked my friends at these IC vendors, the memory companies, why they do this, and their comment is they don't trust their customers. So in the data sheets is a spec for allowable timing skew. You take that number and you figure out how many, you know, mills that is on inner and outer traces added up, and pick a conservative number, and you can make those timing requirements. It's not plus or minus 10 mils.
Right. It's
It's
usually more
something-
like plus or minus a half inch.
Yeah, it's 250 or 500 mils.
That's right.
So serpentine is a pain in the ass, and it costs you money.
That's right.
So
With DDR2 or 3, for example, typical available skew for the address lines or for the data lines is about 1/4 of an inch.
it's a lot better with some of the newer memory technologies because they have smart driver systems
Yes, they
where
do.
they actually go out, you can calibrate your physical transmission lines,
Yeah.
and it can adjust the time when each of the signals is launched.
Right.
And so you can
DDR3
really,
and 4 do that.
yeah, so it's a little more forgiving, but you still want to not go at it with the idea that you need to match something incredibly stupid and end up paying the price in layer count.
Right.
I did a design where the length matching requirement was 0, and this was because it was a pre-silicon emulator, and from the ICs that were doing the signal generation to the connectors, it had to be pretend it was a chip. So the entire timing budget was relegated to the target board. So did we do a lot of serpentining? Yes, but we had a reason to do it.
Right.
Like you said, the timing budget had to be given to the target board,
Right.
just like it was a chip. But in most cases, you know, like I say, they don't trust the customers to know what they're doing, and they want you to be successful. So take that.
Let's go on. John is asking, what are your thoughts about tying circuit return to chassis ground? I think we kind of answered that earlier.
Right.
Yeah, you would want to do that at the I/O connector.
Yes,
A
that's
single
only
point,
at the I/O.
Well, multiple points, like one on each end of the connector at the very minimum.
Well, for a connector, yeah, but I mean,
Oh,
not,
yeah,
not,
yeah,
not
at the
4 different
I/O,
connectors on the board.
Right. I mean, usually when we tie chassis to the signal ground, it's across that whole front end where the connectors are. We'll put several screws in, and then multiple screws from the connectors into the, 2 screws per connector into the board, and all of that kind of, I mean, you end up with several screws attaching the two together.
Yeah, good idea.
It's not a single point, it's an area along the front where the I/O connectors are.
Next question from Neil. What's the rule on connecting the grounds on 2 sides of a cable? For example, HDMI or USB 3. I often see them suggesting inductors on one side, presumably to prevent ground loops. Ugh.
I wouldn't use an inductor.
No, you don't want to put an impedance in any cable shield.
Right.
That's going to create a mode conversion.
Is he talking about the ground lines themselves that are in the cable, not the shield?
Oh, as part of the transmission line.
Right. I mean, if you're going to put ferrites, for example, in the signal lines to filter the signal, and you want to filter the return as well. It's just part of the signal. Correct?
You don't want to put a ferrite in the returns.
I wouldn't use ferrites for anything. No, I never use
actually, let's
okay, all right. But if
let's just say ferrites have an application, but usually not in signal or power buses.
Okay.
Yeah, they're what you do when you can't redesign the system and you got to still ship product.
So if you had to filter I/O, how would you do it?
Common mode choke.
Okay,
but
well, that's
you
Yeah,
definitely
like
don't
in
want to put,
Ethernet, like Ethernet, yeah.
yeah,
yeah.
Or
All right,
CAN.
well, that's fine.
CAN,
Well,
you use a
Ethernet,
common mode choke.
yeah.
Ethernet
Don't,
is differential, and so you can run it out of a signal transformer that also has a common mode choke, and by definition, it's filtered. What do you do with single-ended signals?
Well,
series
there's,
resistor.
So basically a ferrite, like I said.
Series resistor. I would not put a ferrite in a
All
signal.
right.
Yeah,
So a lossy resistor.
yeah, yeah, yeah.
And do you
1K
put the
resistor.
resistor on the return line as well?
No,
Why?
you don't want to put any impedance in any kind of signal or power return.
what are you trying to protect against, though? That would be the
Return
question.
is simply the other side of the transmission line.
Yeah.
You're going to filter one side. Why not filter the other side?
If you're trying to keep from having, signals that are being applied to the cable from farther in the board, you put a capacitor at the connector pins.
Yeah, yeah,
And you don't need anything in series with any of the signals.
That's usually best. Yeah,
Okay,
I would
right.
not on a
If
differential.
if you got bad news happening and you need a transient suppressor, or if there's got a problem for reverse signals, like in the case of automotive, you use a big reverse battery diode. But the bottom line is a capacitor at the cable pin, first line of defense.
Yeah,
And depending on the application and the aggressiveness of the environment, you go to the next levels. At some point, you may need to do what Rick had to do, which is for all their signals, they had to transformer couple them. Either that or optocouple, because you have
Right.
to completely isolate the input signal from the circuit board to keep it from burning up to a crisp.
honestly, the biggest issue I've had with HDMI cables is the fact that they use pigtails to connect the shield back to the connector housing.
Right.
Yeah, so the cables are crap.
Oh, they
And
are.
you
They're
need to
terrible.
buy a good
They're
cable,
terrible.
because you can't fix that on your circuit board.
Right. Well, let's move on.
No, you can't. You got frequency in there again. Go ahead, read it.
Yeah, yeah. Artur is asking, do I still need to match impedance if the length is greater
The length in inches, probably.
in inches?
Greater than
Okay,
an inch, the edge is less than a nanosecond. If it happens once a year and it switches in a nanosecond, it's a gigahertz signal.
Yes.
Yeah,
And
but
if your line,
And you have to match impedance.
if your line is longer than an inch, yes, you need to match impedance.
okay. Okay, moving on. Mark is asking, from the point of view that energy is not traveling through the traces, how should the dimensions of the traces and ground returns be determined for high power signals?
It's about the capacity of the dielectric.
Right.
Yeah, yeah.
How many
You're gonna get
coulombs
heating.
per second can make it through that? If your
Right.
capacity, if you've got 50 ohms and you've got a signal, an energy you're trying to move through it, you can only get a tenth of an amp through 50, a tenth of a coulomb through a 50 ohm transmission line. If you need an amp, you need an impedance of 5 ohms, or you need 10 50 ohm transmission lines. You don't need 3 ounces of copper, because even if you use 3 ounces of copper, you still got a single dielectric. It hasn't increased the capacity. It only means that it can get hotter before it burns up.
And I'm not sure what he means by high power signals. If that's RF power, you probably want to move it from the transmission line within the board to like a coax cable or something.
What I do when I'm moving high energy is I use multiple dielectrics in parallel, and that's the way I've solved that problem. When I move it through the board stack, I use interleave power and ground vias to go from dielectric at the top of the board to the bottom, for example. And then when I move horizontally in the board, if I need significant energy, then I want to use a fairly wide trace across the ground plane. And if, something on the order of giving me 10 or 15 ohms of impedance, If that's not enough, then I put another power conductor underneath the ground plane, and now I've got twice as much capacity and reduce the impedance by half. So I go from 10 ohms to 5 ohms, and that gives me a whole lot more coulombs per nanosecond, which is what I need to move through the board.
Okay,
I'm actually doing a class right now on consumption-based energy management for high-performance ICs.
We've got 9 questions left. Let's see if we can run through them with maybe shorter answers.
Yep, let's do.
Yeah. So, Rick, we're going to put you on the spot here. When is your book coming out?
Probably not. I keep trying to find the time. I retired 5.5 years ago, and I said, "Oh, I'm going to have lots of time now." Boy, was I wrong.
Yeah, I know what you mean.
That's what everybody tells me.
Patrick Andres and my book on EMI troubleshooting took us 18 months, and that's with 2 people working on it.
Oh, I'm not surprised.
Yeah, let's move on. Hopefully your book will come out one of these days.
Well, hopefully before I die. I'm 75 now, so how much time do I have left? I don't know.
Well, you better get with it.
I know.
Ezekiel is asking, what are your thoughts about tying circuit return to enclosure or chassis ground?
We just talked about that.
Yeah, I think we talked about that. If you have a ground structure like a chassis, you want to return or connect the digital return plane to the chassis at the connector.
The I/O.
Yeah. Okay. Jim is asking, it would seem that the circuit and field theory explanations would converge at low frequencies in DC. Am I wrong with this assumption, and which of Mr. Morrison's books addresses this? Well, I think you're exactly right, and I think I touched on that in one of my slides. At DC, pure DC, you're going to have a conduction current through copper, and the electrons move very slowly, but that's what you would measure with an ammeter. Now, as you increase the frequency from DC to, say, the low kilohertz, it's going to transition from conduction current to propagating fields in the dielectric space, and so there's a point probably in the audio frequency range of maybe 10 kilohertz or so that it's definitely going to be, energy movement by fields.
Yes. It's somewhere between 5 and 10 kilohertz that it converts completely to movement by fields.
Yeah.
You still
Dr. Hubing has a good experiment on his, it's probably on his website somewhere.
With the coax and the...
Where he measures the current, the return current, as you increase the frequency between the path of least resistance and the path of least impedance.
Right. Yes.
Yeah.
I've seen that done many times. I've seen Lee Hill do it. I've seen Todd do it. I've seen Tom Van Doren do it. And Todd has a wonderful graph that I present in most of my presentations, which I of course credit to Todd, showing, how things change as frequency goes up.
So it's a gradual transition.
It's a gradual transition. Yes, at 5 or 10 kilohertz,
But you want to follow the rules all the time. You don't really care.
Right. That's exactly right. Follow the rules as if it always matters, because it generally does.
It always matters.
Yeah.
Well, yeah.
Your system will be more robust no matter what frequency.
That's right.
Enrico is asking, is longer trace path on the same layer better than shorter path when switching between layers? That's an interesting question.
If you can move the fields between layers with proper return vias, it's basically irrelevant.
Yeah.
Yeah.
But if you can't, then stay on one layer.
You've got to have
that's a timing issue.
ground transition vias.
Right.
And
if you
because
can't, then stay on.
they're typically such a small discontinuity that that whole idea of the signal being messed up by a via doesn't, there's no inductance, doesn't matter, it's impedance. So
I'll tell you guys though, having said that, the last project I worked on at L3, and you've heard me talk about this, Dan, was a 3x4-inch board with 1,300 and some components on it. Think about that, a 3x4-inch board. There were two 1,300 pin BGAs and 8 other BGAs on this board. It was packed. And there were a lot of places where had we changed layers, we might not have had room for a transition.
for vias, yeah.
Right,
Yeah.
so we tried as much as possible not to change layers.
Yeah, that's a mechanical thing.
Yeah.
But as far as signal integrity and the whole thing about, you know, via stubs and all this stuff, you aren't doing anything on an FR4 board where you care about via stubs. And you certainly aren't going to worry about moving signals around. If you, this just comes to one of the things, a quick touch on HDI. A lot of people are sucked in by the wonder and beauty of HDI. The problem is that it's really difficult to do Z-axis transmission lines, especially if you're going between more than one layer pair with HDI. And it's even more a problem with moving energy because you both thermal, because you have a very small thermal mass connecting your ICs to the ground planes, and to go from a capacitor on the bottom of the board to the top of the board, it's not a straight path anymore that you get when you have two drilled vias next to each other.
Right.
So be careful. I don't use HDI yet. It's better to go to blind and buried vias.
It really depends on the technology, but yeah.
So I'm not sure what Gordon Miller is asking here in his question. What he's saying is above 377 ohms. So that sounds like dV dt in the near field, possibly. Thinking in circuit theory terms, the voltage divider limits energy delivery to an antenna. Can that be described from the point of, from the energy point of view? I'm not exactly sure I'm following that question.
I'm
Free
not either.
space is 377 ohms. It doesn't get bigger than that.
Well, it does in the near field. If your source, if your energy source is changing voltage with time, it can go to 1,000 or 2,000 ohms. But I think Gordon, I would suggest you ask that of one of us, although I'm not sure. Maybe you can rephrase the question and email one of us.
I'm not sure I have an answer.
Yeah. So yeah. Try elaborating on that and then emailing one of us.
Yeah, email all three of us, and we'll see if we can
good
try to
idea.
get an answer.
Good idea. We'll probably have 3 different answers.
Yeah, probably. It's okay.
Okay, moving on. Michael is asking, most of my high frequency designs use coplanar waveguide traces. What would be the optimum via structure to another coplanar structure on the opposite side of a 4-layer board?
Side by side.
Via pair.
Vias.
Yep.
Yeah, I mean.
Yeah, via pairs, definitely.
Yeah. But I don't know about high frequency on coplanar. You can't go very high.
I mean, there are people who do RF boards that are purely coplanar, and sometimes they're very high frequencies. You just have to be very careful.
Yeah, you'd have, it depends on what the driver impedance is.
Yes.
Okay.
Otherwise, it's just going to blast back at you.
That's correct.
Okay, next question. This is rather lengthy. So if a bundled coax leaves the chassis via some sort of I/O connector, the outer shield braid should be an extension of the Faraday cage that is the chassis.
Right.
Okay, so far that's correct. However, you often see a ferrite around the entire cable not far from the connector. Another fair observation.
Yep.
This often fixes the emission problem, I assume, sometimes. But doesn't this just fix bad design of the internals?
Thank
If
you.
Yes.
Thank you.
Yes.
Thank
Our
you.
It's a
point's exactly-
Band-Aid.
You bet it's a Band-Aid.
If the outer shield of the bundle goes through the ferrite, it may impede common mode currents on the bundle caused by the internal signals referencing to the outer shield, but it does lower the effectiveness of the outer shield as a shield.
Well,
no, it doesn't.
mostly what happens is you're allowing the energy to be coupled to the outside of the shield.
Right, because you don't have a good 360-degree attachment of the shield.
And that's where the ferrite comes into play.
That's correct.
Yeah, if it's the correct ferrite.
Yeah, that's where you make all your money. I depend on people like you for that kind of stuff.
Yep. Okay, moving on. Got 3 more questions. Wow. Steve is asking, just a comment, crosshatched planes are recommended in some applications for PCI compliance in terms of securing boards used for payment processing. It helps protect the energy signature of encrypted data, basically turning it into Swiss cheese if somebody tries to sniff the data. Okay,
I think it would cause you would see all those little tiny reflections sort of, but it really wouldn't be as effective as just driving those traces into the inside of the board.
Well, I think he's actually bringing up a point where the crosshatch planes are acting as somewhat of a shield to prevent, to limit the near field.
What's going to keep it changing?
Energy from getting out and allowing somebody else, a bad person, to sniff out your credit card.
I think solid planes do a better job.
I'd love to see more on that. I'd love to see.
Yeah, I think if you used a solid plane in this application, it would shield the near field, the NFC signal too much. I think that's his point.
Well, you wouldn't be able to see it.
Yeah.
I don't know.
Yeah.
That's what you don't want to see.
It's like a leaky coax shield.
Yeah, I think you get 200 dB out of a solid ground plane. I think that.
But it's only a leaky coax shield if the openings are big enough to allow it to be leaky.
Right.
If they're below a 10th wavelength of the maximum frequency, then it still effectively isn't leaky. Right?
Well, I think he's talking about point of sale.
Right.
Stations.
I'm not sure. Maybe we need more about this question.
Yeah,
I'd like to know more about this.
Yeah.
So Steve, send us an email with in fact, if you can, the standard or some of the recommended design guidelines would be interesting to see.
Be great to see.
My guess is it came from a semiconductor vendor, and you know our opinion of that.
Yeah, right.
Yeah, don't trust those guys.
Yeah, exactly.
Yeah, okay. We're all liars. Via impedance.
Okay, the last question. When do I have to consider the via impedance?
First thing, vias do not have impedance. Vias are a single piece of conductor.
When there's
has two vias.
When there's a via pair, they have an impedance.
That's what I'm talking about.
Right. So when do you have to consider via impedance? Is obviously you have to route them in pairs, signals with their returns or power what they return via. And you consider the impedance when the wavelength in decay of the highest frequency is small enough that the length of the via can be a distributed element.
Yes.
And you have to calculate that, and there's no one answer.
You need to see what the switching speed of your driver is, and that's what matters. And the thickness of the via. If it's a 62,000th long via, it takes a pretty high frequency for you to care.
It takes a very high
it becomes very difficult to manage via impedance because based on board thickness, you're limited to how close the vias can be together.
I'll tell you a quick story. When I was in telecom in 1999, we designed our first 10 gigabit system. We didn't know about via stubs. We didn't know about via impedance. We didn't know about any of that. We just designed the board and it worked. You know what I mean?
Yep.
Hey, back
Now,
when
granted,
I started engineering, we were using a wire wrap.
yeah,
Hey, I wire wrapped a 68020 single board computer and thought I was a
can't tell you.
monster. And it
Can't tell you
worked.
how many of those I did when I was young.
Well, guys, oops, wait a minute. We got a
We're
couple.
almost done.
Yeah, just when we thought it was over. Okay, Jim is saying, just a comment, I'm a long retired from large-scale distribution pro audio systems and since have been solving EMC issues in ham radio. I must use lots of common mode chokes to solve issues that are the result of poor design, failure to bond cable shields to enclosure, and even contacts that fail because there's pain in the way. Okay. Agree.
Yes.
Agree. I'm also a ham operator, so I've been bit by RF before I hold the mic up.
This is the legacy of, we had guidelines that were based on what didn't make it fail, not on what was right. And we got away with a lot of stuff that was completely wrong, but it wasn't so wrong that the system wouldn't work.
Exactly.
And we live in a world where you don't get any more, there's no more get out of jail free cards.
Right.
It's do it right or you're going to have to respin the board. And that's where billions of dollars are wasted every year by companies that are forced to respin their boards 3, 4, 5 times because they are not given design rules that are based on the science. And that's the main purpose of this webinar.
Yep.
Is to change that.
That's a great summary. We're not going to take any more questions at this point. I think we need to wrap things up.
Yep, I agree.
So just want to thank Lucy for providing us the opportunity to
Lucy and Sierra Circuits.
And
yes,
Sierra Circuits, yes.
Awesome.
Yep,
Thank
you guys are the best.
Thank you so much for doing this. It was incredible, and people really liked it, according to the comments.
Good.
Well,
good,
I think
good,
we
good.
owe a lot to Ralph, and that's that's really why we're having this seminar, is to offer a tribute to his work through the decades. And thank you, Dan and Rick, for helping me learn, and also
Thank you for
contributing to
helping
this.
me learn. And Dan.
It takes all of us, because if we didn't have anybody to argue with, we wouldn't be able to move forward. We'd be stuck on our own, sometimes correct and sometimes incorrect understanding.
That's
But
true.
we don't have Ralph anymore. And like I told Lucy in the beginning of this, watching the beginning of this presentation, I was crying because I really miss Ralph.
Yeah, I do too. A wonderful man.
I have more questions now than I ever did, and he's not here to answer them.
I know.
We started off with over 250 participants, so we're still almost 80. So you 80 that are still hanging on, you guys are certified geeks.
And if you really want to get into it, the www.ralphmorrison.com is where we posted the videos that we did for his training class, which was reflected on his last book. And just to pitch that, the proceeds from that website, because these are pay-per-view, all go to Elizabeth.
Good.
Thank you. Thank you, everybody. I just unmuted my video. My audio. I was listening to all the wonderful questions. It was just like having Ralph here. So thank you for doing that. It was so nice.
Thank you so much, all of you, for everything.
I know Ralph would have loved to be here.
Oh, I know he would have. God, I miss him.
Thanks to all the participants, too, for your great questions.
Oh, absolutely.
There were so many great questions. So
there were wonderful questions.
If anything, we hope it pushes you to want to go find out more.
Yes.
We aren't perfect, and we still are blinded by what we've done that's successful. And Ralph's understanding was always driven by the physics Rick and Ken and I have done a lot of things that we've found to be successful and some that have not.
Right.
And all we can talk about is, you know, our perspective, and we try really hard to make it as correct as possible. But the issue is that even for us, we've got many years of doing things the way we always did them. And, you know, the push to smaller and smaller geometries and the increased spectrum for compliance and increased energy levels based on, you know, moving to 5G and all the NFC stuff and the increased amount of radiated emissions that are happening around the circuit boards make it much more difficult. And so we're still learning too, but the bottom line is, for us to be successful, the industry has to stop just accepting the fact that they're going to fail EMC. You have to change that perspective.
Right.
I deal with billion-dollar companies. I'm in sales for automotive. And so all the big guys, the tier ones, the OEMs, they all will admit that they spend 3 and 4 times of respinning the boards in emergency. You know, I'm spending expedite charges. I'm begging for time in the chamber so I can do this again, instead of paying for training. They could easily spend 1/10 of what it costs for one module respin to get Rick to come in there and spend a day teaching.
Right. Or you or Ken. I mean, there's any, or Todd or Eric or God, there's.
It would change their world, and the money goes straight to the bottom line.
I know. It is amazing. I think one of the smartest things I ever heard, about 1.5 years ago, I went to Salt Lake City to do some training at a company, 2 days, and the engineer who had arranged for me to come in made it a condition of hiring in the company that they bring you and I, Dan, in for training.
That's great.
And I mean, I was not delighted because they had me come in. I was delighted because he cared enough to do something about it. To not go to a company and just let them go on as usual.
Yeah, I've had a few programs that launched where the OEM told the tier one that one of the requirements for the contract was that they take a class from me.
Yeah, there you go. So it should be. Ken, when are you going to do a public class again? I've really wanted to come to yours as well.
Well,
who knows, right?
Had one scheduled for April, and then we moved it to May, and then we canceled it.
Yes,
Yeah.
that's exactly what happened to me.
Yeah. So I've got a series in May that's webinar based on troubleshooting, not specifically on circuit board design, but hope to have
basically
my regular 2-day seminar in the fall, and we'll talk about PC board design in much more detail.
Right.
But you know, if those of you who are mainly interested in PC board design, I'd recommend Rick or Dan. They give real good tutorials on that.
And a good place to do that would be PCB West.
Yeah,
Good
absolutely.
Point.
I've been every year since I found out about it.
So have I. I've been there every year since 1993.
You must be old.
Oh, I am old.
That's when within 5 minutes of being in Rick's class, I went from being a senior engineer to being scared and confused. It took him 5 minutes to bring me down to my knees.
You should read some of the chats that are ongoing.
Yeah.
Let's see. Jesus has bought. Oh no, Enrico has bought 2 books from Ralph, and Jesus is buying for tickets for PCB West right now.
Yeah, Rick. I've got 5 classes scheduled, and Rick's probably got 6 or 8.
I have 6, I think,
at PCB West. So
yeah.
Okay.
It's not just signal integrity, it's the materials, and that's something I wasn't aware of. You really need to know about the materials and the fabrication technology, because those are your components as well. You know, again, the ICs are nothing. When you want to do a system, you have to have a way to move the energy around. So you're designing dielectrics. and you're using conductors. So you need to know about the technology of that material.
Well, some of our participants are in Europe, so let's let them have dinner or
Oh God, yes.
go to
or
bed.
watch for in Europe.
Let's wrap this up.
Altium is doing a series of events around the world too. So,
yep. Well, guys, it's been
thank you,
great.
everyone.
Thanks, Elizabeth. Thanks,
Thank you,
Lucy,
Lucy,
Sierra.
and thanks,
everybody.
Sierra Designs.
remember,
I love all of you guys.
it's
we're gonna
all
sign
about
off
the
here.
space.
Yes, it is. Thank
It's
you.
all about the
About
space.
the space. About
That's
the
why we
space.
play the song over and over in the beginning, because it's an earworm designed to make you wake up in the middle of the night screaming. It's all about the space.
That's Dan's daughter, by the way, singing that tune.
Yes, it is. His
That's my
beautiful daughter.
23-year-old. Yeah.
Okay.
God, hard to believe she's that old now.
I know. When you met her, she wasn't.
She was a youngster.
Yeah.
Well, goodbye and good night.
Yeah, 6
Yes,
months
love you
space.
all.
Yes.
Thank you again.
Take care,
Cheers to everybody.
Everybody
Thanks,
be safe and
Lucy.
healthy.
Yes, all of you.
Bye-bye.
Love to all.